Now that you understand what a derivative is, and you have one method using limits and the Newton quotient to find a derivative, we're going to spend some time discussing notation. The notation of math for economics is very important because you're going to use that in upper year courses to understand economics in the textbook. You're going to use it to understand economics that your instructor is teaching you in class. So let's take a moment to learn two types of notation. The first is sometimes called prime notation, and the second is called Leibniz notation, and it's important that you know both. The first notation is what I call prime notation, but another formal name for it is Lagrange notation. And it gets its name because it's going to be using an apostrophe, which we sometimes call prime. So if we have a function f of x, then the derivative of this function is f prime x. A quick example, if we have a very simple function, it looks like it's kind of a quadratic function. We've got f of x is equal to x squared. Then we could write the derivative of f of x as f prime. And we would say f prime of x is equal to 2x. Notice in the example I use the word then here. F of x is equal to x squared. From that, it follows that f prime of x must be equal to 2x. A simpler way of writing this is to use an implication arrow. And here are some examples. We've got f of x is equal to x squared, which implies that the derivative of f of x, f prime x, is equal to 2x. We can look at another way of writing this. If we have f of x is equal to 2p minus x, where x is the variable of interest, we could say, well, 2p, p being some constant number, minus x, the whole thing squared. We could expand that out. So we have 4p squared minus 4px plus x squared implies that f prime x is equal to, and I'll continue on the line below, minus 4x plus, that should have been plus 2x. How did I take the derivative so quickly? Well, we'll talk about that in the next series of videos. But for now, let's just focus on this prime notation and the implication arrows. Now that we've learned about prime notation and implication arrows, we can turn to converting from prime notation to Leibniz notation. And so we've got f prime of x, which we defined as the derivative of f of x. And we're going to rewrite this in Leibniz notation. We've got quite a bit of information here, so let's break it down. The first thing is this equation, this equal sign here with 3 horizontal lines instead of 2. This is called an equivalency, and it means just that. It means that f prime of x is equivalent to this thing right here. So that's stronger than just equals to. They are the exact same thing. And in Leibniz notation, it's written as a fraction, always written as a fraction. And the numerator tells us which function we're going to take the derivative of. And so right here, we see we've got df of x. So we're going to take the derivative of f of x. And we're going to take the derivative of f of x with respect to x, which is why we have the dx in the denominator. You can kind of notice that the x and the f of x are in italics, while the d for derivative is not. It's in plain text. We can write it slightly differently over here, also equivalent, means the same thing. we could write the function almost like looks like it's being multiplied by d over dx. And it's not actually being multiplied. This is an instruction that tells us to take the derivative of f of x with respect to x. X is the changing variable. Let's look at an example. We've got f of x is equal to x squared. I can write this using notation in a number of different ways. I could say that f prime of x is equivalent to the Leibniz notation, where instead of just having the placeholder, the general form f of x, we're actually going to write the specific function x squared. And the Leibniz notation tells us that we're going to take the derivative with respect to x. Another way to write that, we could just write it with the command over here, d of dx, says you're going to take the derivative of the function beside this with respect to x. So we're going to take the derivative of x squared with respect to x. When we switch back to the equal sign is when we're actually going to take the derivative. So this is telling us to take the derivative of x squared. When we perform that operation, we get 2x. So this is a command to take the derivative, kind of like the limit operator that we saw in earlier parts of this course. At the beginning of the video, I told you it was important that you know both prime and Leibniz notation. One reason for that is because prime notation is much more convenient to write. It's a little bit shorter, it's a little more compact. But Leibniz notation gives us more detail. It tells us, it specifies what we're taking the derivative with respect to. So it tells us very specifically, if we have f of x, we're going to take the derivative with respect to x. And that can be very useful, especially when you're getting into multivariate calculus, or we're looking at composite functions that we'll be looking at in a few videos.